Behind every pint and bar of premium ice cream is a high-speed factory operation, cranking out frozen perfection by the ton. From rich chocolate coatings to perfectly swirled flavors packed with chunks, Magnum, Ben & Jerry's, and Häagen Dazs are made with intense precision and non-stop automation. In this video, we go inside the frozen heart of the factories that turn sweet dreams into cold reality. The journey begins long before the ice cream bar takes its recognizable shape. At the heart of Magnum's appeal is its dense, creamy ice cream base, typically made from a high butterfat dairy mix that gives it its rich mouthfeel. The base ingredients include whole milk, cream, sugar, glucose syrup, and sometimes egg yolk for additional texture. These raw materials are sourced from vetted dairy farms and suppliers that comply with stringent quality control measures. Upon arrival at the production facility, the dairy ingredients are immediately transferred into refrigerated holding tanks to maintain their integrity. Here, laboratory technicians perform routine tests for microbiological safety, fat content, and pH levels to ensure the base meets the strict specifications required for premium ice cream. Once the ingredients pass inspection, they're pumped into large stainless steel mixing tanks. These tanks are equipped with high-shear agitators that blend the milk, cream, and sugars into a homogeneous mix. During this phase, emulsifiers and stabilizers, such as mono and diglycerides or guar gum, are added to enhance the creaminess and improve the shelf life of the product. The mixture is continuously agitated and brought to a temperature of approximately 60-70 degrees Celsius to fully dissolve the sugars and emulsify the fats. The next critical step is pasteurization. The liquid mix is sent through a continuous flow pasteurizer, usually a plate heat exchanger, where it is rapidly heated to around 83 degrees Celsius for about 15 seconds. This high temperature, short time pasteurization process ensures the destruction of harmful bacteria while preserving the functional properties of the dairy. Immediately after pasteurization, the mix is flash cooled to below 4 degrees Celsius to minimize microbial growth and is transferred to maturation tanks. In the maturation tanks, which are jacketed vessels with slow-moving agitators, the mix is held at low temperatures for 4 to 12 hours. This resting period allows the emulsifiers and stabilizers to hydrate fully and the fat globules to partially crystallize. Maturation significantly improves the whipping quality of the mix and enhances the texture and body of the final ice cream. With the mix properly matured, it is now ready for freezing. The liquid base is pumped into continuous freezers, which are essentially refrigerated barrel drums equipped with rotating scraper blades. As the mix is pumped through these freezers, it is simultaneously aerated and frozen. The aeration, or overrun, is carefully controlled to maintain Magnum's signature dense texture, with overrun values kept well below standard commercial ice cream. The continuous freezer operates at sub-zero temperatures, rapidly freezing the mix to around -5 degrees Celsius while incorporating micro bubbles of air for creaminess. At this semi-frozen stage, the ice cream has reached a soft serve consistency and is now ready for molding. One of the defining features of Magnum bars is their perfectly oval, bar-shaped form. This is achieved using a high-speed rotary molding system. Rows of stainless steel molds, pre-chilled to approximately -30 degrees Celsius, are arranged on a conveyor belt that dips them into a vat of liquid ice cream. As the molds emerge from the bath, the ice cream begins to freeze instantly against the chilled metal surfaces. To ensure a consistent core, the partially filled molds are passed through a hardening tunnel. This tunnel is essentially a blast freezer operating at -40 degrees Celsius or lower, using forced air circulation to rapidly solidify the product. Once hardened, the bars are extracted from the molds using a short burst of warm air or a mechanical press system. Immediately upon demolding, the ice cream bars are affixed to wooden sticks via a precise robotic inserter. These sticks, usually made of sustainably sourced birch or poplar wood, are sterilized and fed into the system through automated dispensers. Now comes one of the most iconic steps in the process: the chocolate enrobing. Magnum's chocolate coating is what sets it apart from most other ice cream bars. The chocolate used is often Belgian in origin and must meet exacting melt and viscosity specifications. It arrives at the factory in solid form and is melted down in jacketed tanks fitted with stirrers that maintain a constant, uniform temperature, typically around 40-45 degrees Celsius, to ensure a smooth flow. The hardened ice cream bars are conveyed toward the enrobing station, where they pass over a curtain of liquid chocolate. Each bar is dipped or showered with the molten coating using a carefully calibrated nozzle system. The chocolate immediately begins to solidify upon contact with the supercooled surface of the ice cream, forming the signature crack when bitten into. To achieve a uniform coating thickness, the enrobing line is equipped with vibration tables and air knives that remove excess chocolate without disturbing the integrity of the shell. Depending on the variant, classic, almond, white, or one of the many seasonal releases, additional toppings like almond pieces, cookie crumbles, or caramel swirls are applied to the wet chocolate shell before it fully sets. These inclusions are dispensed via gravimetric feeders or rotating drum applicators that ensure even distribution. Once enrobed and topped, the bars are transferred into a secondary hardening tunnel for final crystallization. This second blast freezer brings the core temperature of the bar down to around -18 degrees Celsius or lower, locking in the texture and ensuring long-term stability. After hardening, the bars move into the packaging area, a highly automated zone designed for speed and hygiene. Here, the products are first visually inspected, sometimes with the help of AI-based vision systems, to detect any surface defects, asymmetry, or misapplied toppings. Acceptable bars are funneled into flow wrapping machines that wrap each individual bar in a high barrier plastic film. This film is not just for branding and appeal, it plays a vital role in protecting the product from moisture migration, freezer burn, and flavor loss. Each wrapper is pre-printed with product information, including batch codes, manufacturing dates, allergen warnings, and nutritional data. A thermal transfer printer applies dynamic codes as the film passes through the wrapping head. After sealing, the bars are grouped in cartons, often using robotic arm sorters, and packed into corrugated boxes, ready for cold chain logistics. Throughout the production process, quality control is embedded at every stage. Inline sensors measure everything from ice cream viscosity to chocolate temperature, while human inspectors perform taste tests and texture evaluations on random samples. Microbiological swabbing, allergen verification, and weight calibration are also conducted routinely. Any deviation triggers alarms that pause the line until the issue is resolved. This level of scrutiny is necessary, not only to maintain consistency, but to ensure compliance with international food safety standards such as HACCP, ISO 22000, or BRC Global Standard. Once boxed, the finished Magnum bars are palletized and moved into cold storage. These industrial freezers maintain a stable environment at around -25 degrees Celsius, critical for preserving the product's texture and preventing recrystallization. From there, refrigerated trucks equipped with temperature monitoring systems distribute the bars to regional depots, supermarkets, and convenience stores. The logistics chain is tightly managed to ensure the product remains frozen solid all the way to the point of sale. Interestingly, the entire Magnum production system is designed for modularity and scalability. Production lines can be quickly reconfigured to produce different flavors, bar sizes, or seasonal variants, thanks to programmable logic controllers and standardized mold sets. In larger plants, multiple lines may run in parallel, each specializing in a different SKU. Automation doesn't just improve efficiency, it reduces contamination risks and allows for extremely precise control over ingredient ratios, freezing rates, and coating thickness. What makes Magnum truly remarkable is how it bridges artisanal quality with industrial efficiency. Despite being mass-produced, each bar is designed to evoke the sensory richness of a handcrafted dessert. The sound of the chocolate snap, the creaminess of the core, and the exact melting point of the coating are all fine-tuned, using years of research in food science and process engineering. Even sustainability has entered the picture. Many Magnum facilities are now integrating closed-loop water cooling systems, solar-powered equipment, and blockchain-enabled traceability for key ingredients like vanilla and cocoa. This reflects a growing consumer demand for transparency and environmental responsibility, even in the indulgent world of frozen treats. It all begins with the foundational dairy mix, which forms the base for every pint. Ben & Jerry's ice cream is made from cream, condensed skim milk, liquid sugar, and egg yolks. These ingredients are sourced from dairy farms that are part of the Caring Dairy program, a sustainability initiative focused on animal welfare, environmental stewardship, and farmer livelihood. The cream and milk arrive at the factory in insulated tanker trucks, which are sealed and refrigerated to ensure freshness. Each delivery is tested on arrival for butterfat content, temperature, and microbial safety before being offloaded into large, refrigerated stainless steel storage tanks. Once approved, the raw ingredients are metered into blending tanks, where the liquid base is formulated. These tanks are equipped with high-shear mixers and homogenizers that ensure a uniform dispersion of fat and solids. Egg yolks are added not just for richness, but as natural emulsifiers, giving Ben & Jerry's its thick, custard-like body. Depending on the flavor being produced, this base mix may also include cocoa powder, pure vanilla extract, or natural flavorings, each added in precisely measured quantities under strict batch protocols. Every component is logged and traceable, complying with both food safety regulations and the company's transparency standards. Next, the liquid mix is pasteurized to eliminate potential pathogens. This is done through a continuous flow system, typically a plate heat exchanger, that rapidly heats the mixture to around 83 degrees Celsius for about 15 seconds. The mix is then cooled instantly to below 4 degrees Celsius and sent to aging tanks. These stainless steel tanks are fitted with slow-moving paddles to keep the mix from separating while it rests for a minimum of 4 hours, and often up to 12. Aging allows the milk proteins and emulsifiers to fully hydrate, improves the texture, and helps develop the desired mouthfeel in the final product. Once the mix has aged properly, it's time for flavoring and freezing. This is one of the most tightly controlled and choreographed stages in the process. The aged base is pumped into continuous freezers, large barrel-shaped machines that scrape, whip, and chill the mix simultaneously. In these machines, the mix is cooled down to about -5 degrees Celsius and aerated with tiny amounts of air. Ben & Jerry's is known for its super premium designation, which means it contains less overrun than standard ice cream. Overrun refers to the amount of air incorporated during freezing, and low overrun results in a denser, creamier product. The target overrun for Ben & Jerry's is around 20%, far below the 80 to 100% often found in cheaper brands. As the ice cream exits the continuous freezer, it is still semi-soft and ready for the next hallmark of Ben & Jerry's, the mix-ins. The brand's chunky identity relies on adding generous portions of solid inclusions such as cookie dough, fudge brownies, peanut butter cups, and nuts. These ingredients are pre-prepared and kept frozen or chilled to prevent them from melting or breaking apart during mixing. They're delivered to the factory in bulk containers and are inspected for uniformity and contamination. Depending on the flavor, the inclusions are automatically dispensed into the flow of semi-frozen ice cream using an ingredient feeder. This is a sophisticated auger system that evenly meters chunks into the product stream without jamming or crushing them. The swirl elements, like caramel ribbons, fudge streaks, or marshmallow sauces, are added through a separate injection system. As the ice cream flows through a special section of the filler pipeline, precision nozzles inject thick sauces in continuous streams or pulses, depending on the design. This ensures even distribution without blending the swirls into the base, preserving the distinct streaks of flavor that fans love. With all mix-ins and swirls incorporated, the ice cream is now ready for packaging. The semi-solid product is pumped into pre-labeled pints using automatic piston fillers. These fillers are calibrated to deposit exactly 473 milliliters of ice cream into each container with minimal air pockets or overflow. The filling heads descend onto the pint cups with synchronized timing, and sensors detect the proper fill level. The filled pints are then sealed with a foil lid and capped by a high-speed lidding machine. A light pressure press ensures that the lid sits flush, followed by a tamper-evident heat band or film seal in some plants. From here, the pints travel immediately into a hardening tunnel, an ultra-low temperature environment often referred to as a spiral freezer or blast tunnel. Operating at temperatures around -40 degrees Celsius, this tunnel freezes the pints solid in under 30 minutes, using high-velocity air circulation. Quick hardening is critical not only for texture and shelf life, but also to prevent the inclusions from sinking or rising within the pint before solidification. The spiral hardener moves the pints upward or downward along a long helical path, maximizing contact time while minimizing floor space. Once hardened, the pints are conveyed to a packaging line where they are inspected, date-coded, and boxed for shipment. Vision systems and weight sensors perform final quality checks, verifying that labels are correctly applied. Seals are intact, and there are no underweight or overfilled pints. Acceptable pints are collected into cartons, which are stacked onto pallets by robotic arms. These pallets are wrapped in plastic film and stored in cold storage at -25 degrees Celsius while awaiting distribution. Distribution logistics are tightly controlled to preserve the quality of the ice cream. Temperature-controlled trucks transport the product to regional distribution centers, supermarkets, and scoop shops. Each truck is equipped with data loggers that track interior temperatures, and any deviations are flagged as potential compromise points. Even at the point of sale, Ben & Jerry's invests in branded freezers with specific temperature and airflow settings to preserve texture and flavor. While the process is highly industrialized, Ben & Jerry's maintains a close connection to its values. Fairtrade certified cocoa, vanilla, and sugar are used wherever possible. The brownie pieces come from Greyston Bakery, a New York-based social enterprise that employs people with barriers to employment. Many of the flavor developments happen in pilot-scale test kitchens, where new combinations are trialed in small batches before being scaled up. Once a new recipe is approved, the production team carefully adapts it to the factory setting, ensuring that the large-scale version retains the chunky, indulgent characteristics of the original. Clean-in-place systems are another critical component of the factory's operation. Between each production run, especially when switching flavors, the lines must be thoroughly cleaned to prevent cross-contamination. CIP systems flush the internal surfaces of mixers, freezers, pipes, and fillers with a series of hot water, caustic detergent, and sanitizing solutions. These cycles are automated and monitored by sensors to ensure complete sanitation while minimizing water and chemical usage. Factory workers and quality assurance teams play an essential role in the process. From ingredient reception to final packaging, trained personnel conduct sensory evaluations, sample testing, and equipment calibration. Every batch is logged, sampled, and stored for traceability. Flavor consistency is particularly important for a brand like Ben & Jerry's, where fans expect each pint of half-baked or cherry Garcia to taste exactly the same as their last. In recent years, automation and data analytics have further optimized the process. SCADA systems monitor real-time parameters like flow rate, temperature, and mixing speed. If a deviation occurs, alerts are sent to operators who can intervene before a quality problem arises. At the same time, this data is archived for trend analysis and continuous improvement initiatives. Despite all the technology, what sets Ben & Jerry's apart is the commitment to texture, flavor, integrity, and social values. Making a pint of ice cream that contains a half dozen different textures, swirls, and inclusions without compromising on any aspect requires not just precision, but passion. It's not merely about freezing cream and sugar, it's about orchestrating a complex ballet of ingredients, machinery, and people to produce something that brings joy in every spoonful. The process begins with the sourcing of raw ingredients, mainly fresh cream, whole milk, sugar, and egg yolks. Häagen Dazs prides itself on using as few ingredients as possible, which means that the quality and consistency of each one is paramount. The cream and milk are typically sourced from regional dairy suppliers that meet strict quality and animal welfare standards. Upon arrival at the production facility, these dairy ingredients are pumped from insulated tanker trucks into temperature-controlled holding tanks. These tanks maintain the cream and milk at around 2 to 4 degrees Celsius to preserve freshness. Before they are cleared for use, samples from each delivery are sent to the on-site quality assurance lab for immediate testing. These tests measure fat content, microbiological safety, and protein levels to ensure the mix will deliver Häagen Dazs' signature richness. Once the raw ingredients pass inspection, they are moved to large blending tanks equipped with high-shear mixers. These stainless steel vessels allow the controlled integration of the cream, milk, liquid sugar, and egg yolks. Egg yolks are particularly important in Häagen Dazs formulations as they act as a natural emulsifier, helping to bind the fat and water components together into a smooth, stable emulsion. This use of real eggs is a hallmark of the brand's French-style custard base. In some flavors, pure vanilla extract or cocoa powder is added at this stage, depending on the batch being produced. Every ingredient is weighed and logged, and the entire recipe is controlled by a central PLC system that ensures each batch is blended to exact specifications. Following the blending step, the liquid mix is subjected to pasteurization. This critical food safety step involves rapidly heating the mix to about 82-85 degrees Celsius for 15 seconds using a plate heat exchanger. This kills off any potential pathogenic bacteria while preserving the functional qualities of the proteins and emulsifiers. Immediately after pasteurization, the mix is cooled to below 4 degrees Celsius and sent to aging tanks. These tanks, which are usually insulated and jacketed for precision cooling, hold the mixture for 8 to 24 hours. During this aging period, the proteins and emulsifiers fully hydrate and the fat crystals begin to form, a process that is essential to creating the dense, creamy mouthfeel that distinguishes Häagen Dazs from other ice cream brands. Once aged, the mixture is ready to be frozen. The liquid base is pumped into continuous freezers, which are rotating barrel machines designed to freeze and aerate the ice cream simultaneously. Häagen Dazs ice cream is notable for its low overrun, typically around 20% or less. This means that very little air is incorporated during freezing, resulting in a denser, heavier product. This contrasts with standard commercial ice cream, which may contain 100% overrun, effectively doubling the volume through air alone. The continuous freezer chills the mix to about -5 degrees Celsius while blending it with microbubbles of air to achieve the desired consistency. Once the product exits the freezer, it's in a soft serve state, thick enough to hold its shape but still pliable. At this point, any swirl ingredients, flavor pastes, or inclusions such as chocolate chunks or fruit pieces are added. Unlike brands that pack their products with multiple layers of mix-ins, Häagen Dazs tends to focus on refined and restrained combinations. However, for flavors like chocolate chip or dulce de leche, ingredient feeders are used to incorporate solid components without damaging them or disrupting the flow of the product. These feeders use auger screws and synchronized timing to introduce the chunks or ribbons directly into the stream of semi-frozen ice cream, ensuring even distribution. After inclusions are added, the ice cream flows to the filling station. Pints, which are pre-labeled and stacked in a hopper, are automatically placed onto a conveyor system that moves them beneath piston fillers. These fillers are designed to deposit exactly 14 fluid ounces of product into each container. The fill process is timed perfectly to prevent splashing or overfilling, and sensors monitor the weight and height of each pint as it passes. After the pint is filled, a foil seal may be applied to help maintain freshness and reduce freezer burn. Then, the lid is placed using a robotic arm and lightly pressed for an airtight fit. From here, the pints are conveyed into a spiral hardening tunnel, a vertical, corkscrew-shaped blast freezer that rapidly brings the core temperature of each pint down to below -20 degrees Celsius. This freezing must occur quickly to prevent the formation of large ice crystals, which would ruin the smooth, dense texture. The spiral design maximizes surface area and airflow while minimizing the footprint on the factory floor. Depending on production volume and configuration, the tunnel can hold hundreds of pints at a time, moving them slowly along the spiral track for 30 to 60 minutes. Once hardened, the pints exit the tunnel and move into the packaging zone. Each pint is inspected for proper sealing, correct labeling, and visual defects. This inspection process may include optical scanners and machine vision systems that check for off-coloration, misaligned labels, or foreign material. Some facilities also use X-ray systems to detect any hard contaminants that may have entered during the filling process, particularly in flavors with inclusions like nuts or toffee. After passing inspection, the pints are grouped and boxed into secondary packaging, usually corrugated cardboard cases containing 6 or 8 units. These boxes are sealed and barcoded for traceability, then stacked onto pallets by an automated robotic palletizer. Each pallet is wrapped in shrink film to stabilize it for cold storage. The wrapped pallets are moved to a deep freeze warehouse area kept at -25 degrees Celsius, where they await transportation. Distribution of Häagen Dazs products follows a tightly regulated cold chain protocol. Reefer trucks, equipped with real-time temperature tracking, pick up pallets and deliver them to regional warehouses or retail outlets. Any temperature breach in the chain is recorded and flagged, as a product exposed to temperatures above -12 degrees Celsius for prolonged periods risks partial thawing and textural damage. The robust cold chain logistics ensure that every pint maintains the same texture and quality, whether it's eaten in Paris, Tokyo, or New York. Throughout this entire process, food safety and quality assurance teams are deeply involved. Every step, from ingredient reception to final shipping, is documented under a comprehensive HACCP plan. Daily samples are taken from every production run and stored for shelf life testing. Sensory panels evaluate texture, flavor, aroma, and meltdown properties. Microbiological testing is conducted regularly to verify sanitation effectiveness. In the event of any deviation from standards, production can be halted and equipment cleaned using automated clean-in-place systems. Häagen Dazs also invests in sustainable practices wherever possible. Many of their dairy farms operate under environmentally conscious guidelines, and the brand continues to explore renewable energy options for its manufacturing facilities. Water use, waste generation, and energy consumption are tracked and reported as part of the company's larger environmental footprint goals. What's remarkable about Häagen Dazs' production process is how it maintains artisanal quality while operating at global scale. Every pint is the result of a finely tuned interplay between ingredients, equipment, and process control. The use of real eggs and cream, the low overrun, the gentle treatment of inclusions, and the quick freezing spiral tunnel all contribute to a final product that feels indulgent and rich with every bite. And while machines do much of the heavy lifting, people remain at the heart of the operation, checking batches, tasting new formulations, maintaining equipment, and ensuring that every pint lives up to the brand's heritage. In an age where so much food is optimized for speed and cost, Häagen Dazs stands out by elevating the basics. It doesn't chase novelty for novelty's sake. Instead, it doubles down on purity, richness, and consistency, transforming simple ingredients into something decadent through a meticulously managed production process. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve, so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. The production of sunflower oil in modern industrial facilities is a meticulously orchestrated process that transforms raw sunflower seeds into the clear, golden oil commonly used in cooking and food production. This journey begins with the careful selection and preparation of sunflower seeds, ensuring that only the highest quality seeds are processed to produce premium oil. Upon arrival at the processing plant, sunflower seeds are subjected to a rigorous cleaning regimen designed to remove a variety of impurities that may have been introduced during harvesting and transportation. This initial phase is critical, as foreign materials such as soil, stones, plant debris, and metal fragments can compromise the efficiency of the extraction process and the quality of the final product. The cleaning process typically involves several stages, each employing specialized equipment tailored to eliminate specific types of contaminants. The first line of defense in the cleaning operation is the magnetic separator. This device utilizes powerful magnets to attract and remove ferrous metal particles from the stream of sunflower seeds. Metal contaminants can originate from various sources, including harvesting equipment and transport containers, and their removal is essential to prevent damage to downstream processing machinery and to ensure product safety. The seeds pass over or through magnetic plates or drums, where metallic impurities are captured and separated from the bulk material. Following magnetic separation, the seeds proceed to vibrating sieves or screens. These machines consist of perforated plates or mesh screens that oscillate at high frequencies, effectively sorting the seeds based on size and shape. Larger impurities, such as sticks, leaves, and oversized debris, are unable to pass through the screen openings and are thus separated from the smaller, uniform sunflower seeds. The vibration intensity and screen aperture sizes are carefully calibrated to optimize the removal of unwanted materials, while minimizing the loss of viable seeds. To address the presence of denser contaminants like stones and clumps of soil, the cleaned seeds are then routed through destoners. Destoners operate on the principle of density separation, utilizing airflow and vibration to differentiate between heavier impurities and the lighter sunflower seeds. As the mixture is fed onto an inclined vibrating deck, air is blown through the material from below. The heavier stones resist the upward airflow and migrate to the higher end of the deck, where they are discharged, while the lighter seeds are carried by the vibration to the lower end for collection. This process effectively ensures that only clean seeds advance to the next stage of processing. After the comprehensive cleaning process, the sunflower seeds are ready for dehulling, also known as shelling. Sunflower seeds are encased in hard outer shells or hulls that constitute a significant portion of the seed's total weight. These hulls are low in oil content and can impede the extraction process if not removed. Therefore, dehulling is a crucial step aimed at increasing the efficiency of oil extraction and improving the quality of the resulting oil. The dehulling process begins with the conditioning of the seeds to facilitate the separation of the hulls from the kernels. Conditioning typically involves adjusting the moisture content of the seeds through controlled heating or humidification. Properly conditioned seeds have hulls that are more brittle and easier to crack, enhancing the effectiveness of the dehulling equipment. Once conditioned, the seeds are fed into dehulling machines, which employ mechanical forces to crack the hulls. One common type of dehuller is the centrifugal sheller, which uses a rotating impeller to hurl the seeds against a hard surface, causing the hulls to fracture upon impact. Another method involves the use of roller mills, where seeds pass between counter-rotating rollers that exert compressive and shear forces, breaking the hulls without damaging the kernels. The choice of dehulling equipment depends on factors such as seed variety, desired throughput, and specific plant configurations. Following the cracking of the hulls, the mixture of kernels and shell fragments undergoes a separation process to isolate the oil-rich kernels. This separation is typically achieved through a combination of aspiration and screening techniques. Aspiration involves the use of air streams to lift and remove the lighter hull fragments from the heavier kernels. The mixture is fed into an aspirator, where a controlled airflow lifts the less dense hulls away from the denser kernels, effectively segregating the two components. Screening may also be employed, utilizing vibrating screens with specific mesh sizes to further refine the separation based on particle size and shape. The efficiency of the dehulling and separation processes is paramount, as incomplete removal of hulls can lead to increased fiber content in the oil, affecting its clarity and stability. Moreover, residual hulls in the meal byproduct can diminish its nutritional value and marketability as animal feed. Therefore, processors often implement multiple passes through dehulling and separation equipment to achieve optimal results, balancing the trade-offs between processing time, energy consumption, and product quality. With the sunflower kernels now isolated and free from their hulls, they are ready to undergo further processing to extract the valuable oil contained within. The next stages involve mechanical pressing and/or solvent extraction, each with its own set of procedures and equipment designed to maximize oil yield and quality. These processes will be explored in detail in the subsequent sections, delving into the intricacies of transforming cleaned and dehulled sunflower seeds into the refined oil that reaches consumers worldwide. Now it's time to go into the core phase of sunflower oil manufacturing, the oil extraction process. This is where the golden liquid locked inside the sunflower kernels is separated and collected. The extraction phase typically uses one of two methods, or more commonly, a combination of both, for optimal oil recovery: mechanical pressing and solvent extraction. Each method has its own benefits and limitations, and modern sunflower oil factories are designed to seamlessly integrate these systems into a continuous, high-efficiency process that minimizes waste and maximizes yield. The first step in oil extraction is mechanical pressing, often referred to as expelling. In this process, the dehulled and cleaned sunflower kernels are conveyed into a series of screw presses, also known as oil expellers. These heavy-duty machines consist of a cylindrical barrel housing a rotating helical screw shaft. As the kernels are fed into the expeller from one end, the screw shaft compresses them with increasing pressure as they travel along the barrel. The space between the screw and the barrel gradually narrows, intensifying the pressure and causing the oil to be forced out through small perforations or slits in the barrel wall. This process is incredibly robust and continuous, with some industrial presses capable of handling several tons of seed per hour. However, mechanical pressing alone can only extract about 85% to 90% of the total oil content from sunflower seeds. The remaining 10% to 15% stays trapped in the pressed cake, a solid, fibrous byproduct that still contains a considerable amount of valuable oil. To retrieve this remaining oil and improve overall efficiency, factories employ solvent extraction. Before the solvent extraction phase begins, the pressed cake from the mechanical expeller must be properly prepared. This involves breaking the compacted cake into smaller, uniform pieces using a cake breaker or flaking mill. The flakes are then conveyed to a conditioning unit where they are heated to a specific temperature, usually between 60 to 80 degrees Celsius. This heating not only helps to soften the cell structure of the material, but also enhances the effectiveness of the solvent by improving oil solubility and fluidity. Once conditioned, the sunflower cake is fed into a continuous extractor, typically a horizontal rotary extractor or a loop extractor. In this large stainless steel apparatus, the cake is soaked with a food-grade solvent, most commonly hexane, which has an exceptional ability to dissolve oils. the cake moves slowly through the extractor on a perforated conveyor belt or through a series of baskets, while the solvent is sprayed from above and recirculated from below. As the hexane seeps through the material, it dissolves the residual oil, forming a solution known as micellar. This micellar, containing both oil and solvent, is then pumped out of the extractor and sent to a series of distillation units where the solvent is evaporated and recovered, leaving behind the crude sunflower oil. The evaporation process is conducted under vacuum and controlled heating conditions to ensure complete solvent recovery without degrading the oil. Simultaneously, the now oil-depleted cake, referred to as spent meal, is conveyed to a dissolventizing toaster. This equipment uses steam and indirect heat to remove any residual hexane from the meal, making it safe for use as high-protein animal feed. Next, let's look at the processing of crude sunflower oil, which, at this stage, is a deep amber liquid that contains several impurities, including free fatty acids, phospholipids, pigments, waxes, and trace metals. Though technically oil, this unrefined product is not yet suitable for cooking or bottling. It must be purified and stabilized through a multi-step refining process, which includes degumming, neutralization, bleaching, dewaxing, and deodorization. The first of these refining steps is degumming. In this phase, the crude oil is mixed with a small amount of water or a weak acid, such as citric or phosphoric acid. This causes the naturally occurring phospholipids, also known as gums, to become hydrated and coagulate into a heavier phase that can be separated through centrifugation. The removal of these gums is crucial because they can contribute to off flavors, reduce shelf life, and interfere with further refining stages. The centrifuges used here operate at extremely high speeds, up to 5,000 revolutions per minute, creating centrifugal forces strong enough to separate even microscopic droplets and particles. Once degummed, the oil is subjected to neutralization, where it is treated with a caustic soda solution to remove free fatty acids. These acids can contribute to rancidity and reduce the oil's stability, so their removal is vital for producing a high-quality, shelf-stable product. The soda reacts with the free fatty acids to form soap stock, which is then separated from the oil via another round of centrifugation. The soap stock may be further processed into industrial byproducts such as lubricants or fatty acid distillates, ensuring minimal waste. Now it's time for the bleaching phase. Despite its name, this stage does not involve any chlorine or harsh chemicals. Instead, the oil is mixed with an adsorbent clay material, often activated bleaching earth or acid-activated bentonite, that binds with pigments, trace metals, and other unwanted compounds. The mixture is then heated under vacuum and passed through a filtration system where the spent clay is removed, leaving behind a visibly lighter oil. The objective of this step is not only to improve the color, but also to remove pro-oxidants and residual contaminants that could impact the oil's flavor or stability. But up next is one of the most temperature-sensitive and critical steps: dewaxing. Sunflower oil naturally contains waxes that, while harmless, can cause cloudiness or sedimentation when the oil is refrigerated or stored at low temperatures. To ensure crystal clear oil, particularly for use in transparent bottles, the dewaxing process is implemented. The oil is cooled gradually in a crystallization tank to allow waxes to solidify, and then pass through chilling filters or plate and frame filter presses. The solidified waxes are captured by the filter media and removed, leaving the oil with improved cold stability and clarity. Finally, the last refining step is deodorization. This process removes volatile compounds, including aldehydes and ketones, that can impart undesirable flavors and odors to the oil. Deodorization is carried out in a high vacuum, high temperature distillation column where the oil is subjected to steam distillation at temperatures between 180 to 240 degrees Celsius. The high temperature causes the volatile substances to evaporate, and the vacuum ensures they are swiftly removed from the system. Modern deodorization systems include structured packing and multiple stripping trays that allow for efficient steam-oil contact with minimal thermal degradation of the oil. The end product of this exhaustive refining sequence is a brilliant, light yellow, odorless oil with a neutral flavor and excellent oxidative stability, qualities that make it ideal for cooking, frying, baking, and use in processed foods. The refined sunflower oil is now ready for bottling or bulk packaging, depending on its intended application, whether destined for supermarket shelves or as an ingredient in snack foods, margarine, or ready-to-eat meals. The oil's journey from seed to bottle is far from over. Now it's time to explore the next critical phase in the industrial sunflower oil production process, the packaging and distribution stage. After undergoing extensive cleaning, pressing, solvent extraction, and refining, the sunflower oil is now fully processed, brilliant in clarity, neutral in flavor, and stable for both cooking and long-term storage. But before it can reach consumers or be used by food manufacturers, the oil must pass through highly automated and carefully controlled packaging systems. These systems are designed to maintain product integrity, optimize shelf life, and meet regulatory and commercial requirements for both retail and industrial distribution. Once the refined sunflower oil leaves the deodorizer, it is pumped into large stainless steel holding tanks. These tanks are equipped with inert gas blanketing systems, typically using nitrogen, to prevent oxidative degradation of the oil. Even trace amounts of oxygen can initiate rancidity, so maintaining a low oxygen environment in storage is critical. The tanks are also thermally insulated and often jacketed for temperature control, maintaining the oil at a stable range of around 25 to 30 degrees Celsius. This ensures that the oil remains fluid and clear, preventing cloudiness that could otherwise form during cooler storage conditions. From these storage tanks, the oil is directed via stainless steel pipelines to the packaging area. The transfer lines are equipped with positive displacement pumps and high sensitivity flow meters to ensure precise, consistent delivery volumes. Before entering the filling systems, the oil passes through final filtration units, often made up of multi-layer stainless steel mesh or polymer filter cartridges to capture any microscopic particulates that may have entered during tank storage. This guarantees that only the cleanest, crystal clear oil reaches the packaging stage. The packaging line is often separated into two main tracks, one for retail-sized bottles, typically ranging from 500 milliliters to 5 liters, and another for bulk containers, such as 20-liter jerry cans, 200-liter drums, or 1,000-liter intermediate bulk containers for industrial clients. The retail packaging line begins with empty bottles being loaded onto a conveyor, either manually or through robotic depalletizers. These bottles are usually made from food-grade PET and are blow molded on-site or sourced from specialized suppliers. Before filling, every bottle passes through a bottle rinser, where a jet of filtered, compressed air or ozonated water is sprayed inside to remove any dust or particles. This ensures microbiological and particulate cleanliness before the oil is introduced. The cleaned bottles are then transferred to multi-head volumetric or gravimetric filling machines. These high-speed machines, capable of filling up to several hundred bottles per minute, are calibrated to extreme accuracy, ensuring every bottle contains the precise labeled volume, no more, no less. The filled bottles are immediately capped by rotary capping machines, which place and tighten tamper-evident screw caps or snap-fit closures. Some systems integrate induction sealing, where a foil liner inside the cap is sealed to the bottle mouth using electromagnetic energy. This creates an airtight, tamper-proof barrier that preserves freshness and prevents leakage during transit. After capping, bottles pass through labelers that apply pressure-sensitive or shrink-sleeve labels. These labels are printed with brand information, nutritional facts, batch codes, and expiration dates using high-speed inkjet or laser coders, allowing for complete traceability of every unit. Following labeling, bottles proceed through automated inspection systems equipped with cameras and sensors that verify fill levels, cap integrity, label alignment, and code legibility. Any non-compliant bottles are automatically rejected via pneumatic arms into separate bins for rework. Approved bottles continue along the line to automated cartoning and case packing stations, where robotic arms place them into cardboard cartons, followed by case sealing with hot melt glue or tape. For bulk packaging, a separate line handles large volume containers. These containers are positioned under filling nozzles that are often suspended from load cells to ensure accurate weight-based filling. Bulk fillers must also incorporate anti-foaming and venting mechanisms to prevent air entrapment, especially at high flow rates. Once filled, containers are sealed with heavy-duty caps or tamper-evident seals and palletized for shipping. All packaging configurations, whether for retail or industrial use, are assigned unique identifiers linked to the master production batch and logged in the plant's ERP system. Now it's time to delve into the logistics and distribution chain, which plays an equally crucial role in maintaining the sunflower oil's quality and ensuring timely delivery to global markets. Once the packaged oil is palletized, it is moved via autonomous guided vehicles or forklifts to climate-controlled storage warehouses. These warehouses are designed for high throughput and efficient inventory turnover. Pallets are organized using barcoded location systems, and warehouse management software ensures that the oldest batches are shipped out first, following the FIFO principle. Transportation from the factory to distribution centers, wholesalers, retailers, or export terminals is typically conducted in temperature-regulated trucks or intermodal containers. For export shipments, ISO tank containers or food-grade flexi-tanks are used to transport sunflower oil in bulk volumes over long distances, often across continents. These tanks are insulated and equipped with inert gas blanketing systems to maintain oil stability during the journey. For local or regional deliveries, finished product pallets are shrink-wrapped, strapped, and loaded into trucks equipped with GPS tracking and real-time temperature monitoring. Each shipment includes digital delivery documents with QR codes or RFID tags that sync with customer inventory systems, facilitating seamless unloading and tracking upon arrival. Delivery confirmation, quality checks, and real-time feedback mechanisms are used to verify that every order arrives in optimal condition, both physically and chemically. But up next is one of the most critical dimensions of the modern sunflower oil industry: quality assurance and regulatory compliance. The food-grade nature of edible oil necessitates adherence to stringent quality standards at every stage of the process, from seed selection to final bottling. Every batch of sunflower oil is subjected to a comprehensive suite of analytical tests conducted in on-site laboratories or accredited third-party labs. These tests include parameters like free fatty acid levels, peroxide value, aniseidine value, color, moisture content, and soap residue, all of which provide a comprehensive snapshot of oil quality and stability. Gas chromatography is used to profile fatty acid composition, ensuring the oil meets the standard range for linoleic and oleic acid contents. Spectrophotometers analyze color and clarity, while Carl Fisher titration determines residual moisture. These tests not only guarantee regulatory compliance with international standards like Codex Alimentarius, the European Union Food Safety Directives, and the US FDA guidelines, but also help refine internal production protocols. If any parameter falls outside the accepted range, the affected batch is isolated and either reprocessed or discarded. Up next, we focus on one of the more overlooked yet incredibly vital components of sunflower oil production: byproduct utilization and factory process integration. Modern industrial sunflower oil facilities are designed not only to produce refined oil efficiently, but also to capitalize on every possible output from the sunflower seed itself. This means that even materials which, in earlier generations of oil production, may have been considered waste, are now valuable raw materials for secondary industries or reprocessed within the factory. One of the most important of these byproducts is the sunflower meal or cake that remains after the oil has been extracted. This dense, protein-rich substance is collected immediately following the dissolventizing process and cooled using air blast or counterflow cooling systems to bring the temperature down from over 100 degrees Celsius to ambient levels. This temperature drop is necessary to preserve protein quality and prevent mold growth during storage. The cooled meal is then ground into a uniform particle size using hammer mills or roller mills and passed through vibrating screens to remove any oversized clumps. Sunflower meal is widely used in the livestock and poultry industries as a valuable feed ingredient due to its high protein content and favorable amino acid profile. Factories that produce sunflower oil at scale often have integrated bagging or bulk loading systems for the meal, allowing it to be packaged into 25 or 50 kilogram bags or loaded into bulk silos for shipment in trucks and rail cars. Some facilities even have in-house pelletizing systems that compress the meal into pellets, which are easier to handle, store, and transport. Another byproduct generated during processing is the husk or hull removed during the dehulling stage. These hulls, although devoid of oil and low in protein, have significant value as a biomass fuel. Many sunflower oil factories have transitioned to using these hulls as a renewable energy source to generate heat or steam for use in the facility. The hulls are fed into biomass boilers equipped with particulate filters and emissions control systems where they are combusted cleanly and efficiently. The steam produced powers heat exchangers for oil refining processes like bleaching, deodorization, and de-waxing, reducing reliance on fossil fuels and lowering the factory's carbon footprint. In more advanced facilities, excess steam from the hull-fired boilers is also used to drive small steam turbines, generating on-site electricity that supports lighting, automation systems, and auxiliary equipment. This form of cogeneration enhances energy efficiency and contributes to the plant's sustainability targets. Some operations even sell surplus energy back to the local grid, turning what was once a waste product into a revenue stream. Water recycling is another critical area of integration. Given the extensive use of water in processes such as conditioning, steam generation, equipment washing, and degumming, a closed-loop water treatment system is essential. Wastewater from the plant is collected in large settling tanks, where solids are removed via sedimentation. The water then passes through biological treatment units and membrane filtration systems, such as reverse osmosis or ultrafiltration, to remove organic matter, oil residues, and chemical impurities. The treated water is reused in non-critical applications like boiler feed or equipment cleaning, drastically reducing freshwater consumption. Now turning to process automation, modern sunflower oil facilities operate as highly digitized environments where real-time data governs every aspect of production. Centralized control rooms equipped with HMI panels and SCADA systems provide operators with full visibility and control over temperature, pressure, flow rate, and other parameters at each processing step. Every sensor in the system, from tank-level monitors to flow meters and load cells, is networked to a control system that not only logs data for traceability, but also actively regulates inputs to maintain optimal efficiency. For example, if a temperature deviation is detected in a deodorization column, the SCADA system can automatically adjust the steam valve opening percentage to correct the temperature within seconds. Similarly, in the filling line, digital vision systems detect the fill level and reject any bottles that fall outside preset tolerances. This integration between mechanical systems and digital controls ensures the factory runs continuously with minimal human intervention, reducing errors and improving consistency. Predictive maintenance is another application of advanced automation in sunflower oil production. Vibration sensors, thermographic cameras, and acoustic monitors are placed on motors, gearboxes, pumps, and bearings to detect wear patterns long before failure occurs. The data is fed into AI-driven platforms that analyze trends and forecast the optimal time for maintenance. This prevents unplanned downtime, increases equipment lifespan, and maintains uninterrupted production flow. Inventory management and logistics are similarly digitized. Raw materials, finished oil, packaging supplies, and maintenance components are tracked using barcodes or RFID tags that interface with the plant's ERP system. This allows real-time monitoring of stock levels, automatic reordering when thresholds are reached, and optimized production scheduling based on available resources and demand forecasts. Finished goods are tracked through the entire supply chain, and shipping documents are generated automatically, reducing paperwork and human error. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of liters of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, the truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count, or ATP bioluminescence test, evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 liters in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids, before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. Pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HDST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes, ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes, where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air, which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the deaeration stage. Despite all precautions taken during processing, the condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Deaeration also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Deaeration is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per liter. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a 2-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seam seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in 2 operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life, often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than plus 1 G. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In-store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction. Industrial sugar production begins with harvesting, and depending on the region and facility specialization, the factory will receive either sugarcane or sugar beets. These two crops require distinct processes to extract sucrose, though many of the underlying steps, washing, crushing, juice clarification, and concentration, are similar in principle but differ in machinery, timing, and chemical inputs. Let's start with sugarcane. Sugarcane is a tall, fibrous grass grown in warm, tropical climates. It is harvested either manually, using machetes, or mechanically using harvesters that cut the stalks and strip the leaves in a single pass. Once cut, the cane begins degrading immediately, so it must be delivered to the processing facility quickly, typically within 24 to 48 hours, to preserve sucrose content and prevent microbial activity that would convert sugar into acids. The cane arrives at the factory by truck and is offloaded into massive intake yards. These yards are equipped with cranes or grab loaders that lift entire truckloads of cane and dump them onto conveyors that feed the primary cleaning line. Before any juice can be extracted, the cane must be washed to remove soil, leaves, and insects. This is accomplished with a combination of rotating drum washers and high-pressure spray systems that bathe the stalks in recycled processed water. The water itself is filtered and reused in a closed-loop system to reduce environmental impact. Once clean, the cane is conveyed to a chopper station. Here, high-speed rotating blades slice the cane into short sections to expose the inner fibrous material. The chopped cane then moves through a shredder, a powerful hammer mill type machine that tears the cane into finer particles. This dramatically increases the surface area of the plant material, making the sugar easier to extract in the next stage, milling. The shredded cane is now ready for juice extraction via mechanical milling. This takes place in a series of large, heavy-duty roller mills, typically arranged in a tandem line of 5 to 7 stations. Each station consists of 3 rollers, 2 lower and 1 upper, that compress the cane with immense pressure. As the cane passes through each station, more juice is squeezed out. Water is sometimes sprayed onto the crushed cane, a process called imbibition, to help wash out more sucrose during the final passes. The resulting juice, known as mixed juice, is a cloudy, pale green liquid that contains not just sucrose, but also fibers, proteins, organic acids, and soil particles. What remains of the cane after this process is a dry, fibrous residue known as bagasse. Rather than being discarded, bagasse is transported to a boiler house where it is burned as fuel to generate steam and electricity for the plant itself, often making the facility energy self-sufficient. Meanwhile, the mixed juice moves to the clarification phase. Before sucrose can be crystallized, impurities need to be removed. The first step is heating. The juice is pumped through a series of shell and tube heat exchangers to bring it up to around 105 degrees Celsius. This temperature helps precipitate some of the colloidal particles and also prepares the juice for chemical treatment. In the next stage, the juice is sent to a reaction tank where lime, typically calcium hydroxide, is added. This raises the pH of the juice and helps neutralize acids, precipitate proteins, and coagulate other impurities. The exact dosage of lime is tightly controlled using inline pH meters and flow-regulated injection systems. Flocculants may also be added at this stage to help bind the fine particles into larger clumps. After chemical treatment, the juice enters a clarifier, a large settling tank where gravity separates the solids from the liquid. The solids, known as mud, settle to the bottom and are periodically removed through rotary scrapers and pumped to a filter press where the water content is removed. The resulting cake is either composted or used as a soil amendment. The clarified juice, now a light amber color and much cleaner, is drawn off from the top of the clarifier and sent to the next phase, evaporation. Let's now consider the sugar beet process, which starts quite differently. Sugar beets are harvested using machines that dig them from the soil and remove most of the leaves and dirt. At the factory, the beets are washed in flumes, long channels of water that carry the beets through a series of mechanical washers and screens. Stones and heavy debris are removed using density separation, while fine silt is filtered out with mesh drums and hydrocyclones. Once clean, the beets are sliced into thin strips called cossettes. These are fed into a diffuser, a long vertical or horizontal tank where hot water is sprayed over the beet slices. The water temperature is controlled to around 70 degrees Celsius and flows countercurrent to the beet material, maximizing sugar extraction. The sugar diffuses from the plant cells into the water, forming raw beet juice. This juice is then pumped to its own clarification stage, where lime and carbon dioxide are used in a process called carbonation. Calcium carbonate forms during the reaction and binds impurities, which are then filtered out, leaving behind a clarified beet juice ready for concentration. Both the cane and beet clarification processes converge at this point. They now have a clean, thin juice rich in dissolved sucrose. The next step in both methods is evaporation, which we'll explore in full detail in the following section. But for now, we've completed the complex, high-volume, highly monitored beginning of sugar manufacturing, where plant material is transformed, filtered, and chemically prepared for crystallization. Every moment of this phase is controlled with real-time feedback systems, mechanical separation equipment, and chemical treatments that must be perfectly balanced to set the stage for pure, white sugar to eventually take form. With the clarified juice now prepared, whether from sugarcane or sugar beets, the next major operation in industrial sugar production begins: evaporation. This process is designed to concentrate the diluted juice, which at this stage contains roughly 12 to 16% sucrose by weight, into a thick syrup known as thick juice or syrup, with a sucrose content of about 60 to 70%. The transition from thin juice to syrup is achieved by removing most of the water through a carefully staged thermal process. This concentration step is not just about volume reduction, it also creates the right conditions for crystallization to occur later with control and precision. Evaporation in a sugar factory is typically carried out using a multi-effect evaporator system. These systems are composed of 5 to 6 large vertical vessels, known as effects, connected in series. Each effect operates at a slightly lower pressure than the one before it, allowing the juice to boil at progressively lower temperatures. This setup significantly improves energy efficiency. Steam generated in one effect is reused to heat the next, conserving thermal energy throughout the process. The clarified juice enters the first effect and is heated with steam to just above its boiling point, typically around 115 degrees Celsius. As the juice boils, water vapor is released and rises to the top of the vessel, while the increasingly concentrated juice remains below. The steam from this first vessel is then routed into the heating coils of the second effect, where it causes the juice in that chamber to boil at a slightly lower temperature due to its reduced pressure. This cascading effect continues through all stages, progressively concentrating the juice without requiring additional high-pressure steam inputs at each stage. Throughout this process, automated sensors track the Brix value, sugar concentration, temperature, and pressure in each vessel. Flow controllers and level sensors regulate how much juice is transferred from one effect to the next, ensuring consistent residence time and thermal exposure. Operators monitor these values from a centralized control panel equipped with real-time displays and alarms. If any chamber's temperature deviates beyond acceptable limits, the system automatically adjusts steam input or juice flow to compensate. By the time the juice exits the final effect, it has thickened into a dense, amber-colored syrup with a viscosity similar to honey. It now contains upwards of 65% sucrose and has a reduced water activity, which helps to stabilize it against microbial spoilage. At this point, it's ready to enter the crystallization phase, a controlled process designed to coax sucrose molecules out of solution and into solid form. Crystallization begins in large, jacketed vacuum pans. These are vertical, cylindrical vessels where the thick syrup is further boiled under vacuum to lower the boiling point and prevent caramelization or degradation of the sugar. Reducing pressure allows boiling at temperatures around 60 to 70 degrees Celsius, preserving product quality. Inside each pan, agitators or stirrers keep the syrup moving, while high surface area heating coils provide uniform thermal input. The process begins with the introduction of a small amount of fine sugar crystals, called seed crystals or slurry. These seeds serve as nucleation sites around which sucrose molecules begin to gather and grow. The timing and uniformity of seeding are crucial. If seeded too early, too many crystals form, resulting in fine-grained sugar. If done too late, oversized or irregular crystals can result, affecting yield and downstream processing. Once seeded, the vacuum pan is held at a steady boil, and the syrup is gradually fed into the vessel in a process known as strike feeding. As more syrup enters, the crystals continue to grow while the water content is simultaneously reduced by evaporation. Operators closely watch the strike through sight glasses or by withdrawing small samples to examine crystal size and consistency under polarized light. When the desired crystal size and saturation level are reached, the strike is dropped, transferred to a large horizontal vessel called a crystallizer. Here, the mass, now called massacute, is gently stirred and cooled over several hours to allow further crystal growth and uniformity. The goal is to achieve maximum recovery of sucrose in solid form, leaving behind a thick mother liquor known as molasses. Once cooled and matured, the massacute is ready for centrifugal separation. Industrial sugar centrifuges are large, high-speed machines with perforated baskets that spin at up to 1,200 revolutions per minute. When the massacute is loaded into the centrifuge, the force of spinning flings the liquid molasses through the perforations, while the denser sugar crystals remain behind. Water or steam is sprayed onto the sugar during spinning to remove any residual molasses and improve crystal brightness. After spinning, the raw sugar is discharged from the centrifuge as damp, tan-colored granules. If the plant's end product is raw sugar, for example, in a raw cane sugar mill, this product is conveyed to dryers and then bagged or bulk loaded for transport to a separate refinery. However, in a full refining operation or beet sugar plant, further purification steps are carried out to produce white, food-grade refined sugar. The raw sugar is sent to a melter where it is dissolved in hot water to form a clear sugar liquor. This liquor undergoes multiple filtration steps, including activated carbon treatment and phosphatation or carbonatation, depending on the process. These methods remove colorants, organic compounds, and trace minerals. In the case of carbonatation, lime and carbon dioxide are added to form calcium carbonate, which binds impurities and is filtered out. After decolorization and final filtration, the sugar liquor is sent through a second crystallization stage, nearly identical to the one used for raw sugar, but this time targeting higher purity and clarity. The white sugar crystals formed in this process are sharper, brighter, and finer than raw sugar and are typically centrifuged, washed, and dried in a fluidized bed dryer. This dryer suspends the crystals on a bed of warm air that circulates through the granules, gently removing moisture without breaking the crystals. The final product is pure, white granulated sugar with a typical purity of 99.9% sucrose. It is cooled to ambient temperature and stored in silos constructed of stainless steel or food-grade plastic, protected from moisture and pests. These silos are equipped with temperature and humidity sensors, along with vibrating floors or fluidizing systems to prevent caking or compaction during long-term storage. From here, sugar can be packed into a wide variety of formats: retail-sized paper bags, industrial bulk sacks, or even liquid sugar totes, depending on customer requirements. All packaging is done in cleanroom grade conditions, using automated lines that fill, weigh, seal, and label each unit with production codes and batch tracking information. So far, we've followed the process from raw juice to pure sugar, navigating evaporation, crystallization, centrifugation, and drying. The next segment will explore how factories handle byproducts like molasses, manage energy usage with bagasse or beet pulp, and maintain food safety, quality assurance, and environmental compliance throughout continuous 24/7 operations. Now that the core crystallization and drying stages of sugar manufacturing have produced refined, food-grade white sugar, the final phases of the industrial process turn to three key pillars: byproduct management, energy and sustainability practices, and rigorous quality control systems that ensure every grain of sugar meets the specifications for purity, safety, and consistency. Modern sugar factories are not only high-output food production plants, they are also vertically integrated resource management systems designed to handle waste, generate energy, and produce multiple co-products with commercial value. Let's begin with molasses. After the centrifugation stage, once sugar crystals have been separated from the remaining syrup, what's left behind is a dense, dark, viscous liquid, molasses. This mother liquor still contains residual sucrose along with glucose, fructose, organic acids, minerals, and other non-crystallizable solids. The amount and composition of molasses can vary based on the raw material, cane or beet, the efficiency of crystallization, and the desired yield of refined sugar. In cane sugar operations, molasses is often drawn off after the second or third crystallization strike. Rather than being discarded, it's routed to molasses storage tanks, where it is either sold as a feedstock for ethanol distilleries or used as livestock feed due to its high energy and nutrient content. In some facilities, molasses is further processed to extract minor quantities of sugar through high-efficiency ion exchange or chromatographic separation. But this is only economically viable at large scale, or where sugar recovery is subsidized. In beet sugar production, molasses has a different profile, slightly lower in fermentable sugars, but rich in betaine and other organic compounds. It is also collected in holding tanks and transported in heated tanker trucks to fermentation plants, where it can be used in the production of yeast, citric acid, or industrial ethanol. In all cases, the molasses is handled under strict hygienic conditions to prevent spoilage or microbial contamination. Another major byproduct of sugar processing is bagasse, the fibrous, woody material left over from crushing sugarcane stalks. Rather than treating it as waste, factories utilize bagasse as a biofuel. It is burned in high-pressure boilers to generate steam, which is then used to power turbines that produce electricity for the entire sugar mill. Many sugar plants operate as self-sufficient cogeneration facilities, producing not only enough power for internal use, but also exporting surplus energy to nearby grids. Bagasse combustion systems are outfitted with flue gas scrubbers, electrostatic precipitators, and ash management systems to minimize air emissions and collect residual ash. This ash, in turn, may be used in agriculture as a soil amendment due to its mineral content. or it may be mixed with other waste materials to create compressed fuel briquettes. Some advanced mills pelletize dried bagasse for sale to industrial burners or biomass energy producers. Beet processing also generates fibrous residues, known as pulp. After the sugar has been extracted in diffusers, the beet pulp is pressed to remove excess moisture and then sent to drying systems, usually rotary drum dryers or flash dryers. The resulting dried beet pulp is then either pelleted or ground into flakes and sold as animal feed, particularly for cattle. High in fiber and moderately sweet, beet pulp is valued in the livestock industry for both energy and palatability. In both beet and cane facilities, the wastewater generated during washing, evaporation, and cleaning operations must be treated before discharge. Factories operate full-scale wastewater treatment plants that include sedimentation tanks, anaerobic and aerobic digesters, pH correction units, and sometimes membrane filtration. These systems are monitored continuously using turbidity sensors, chemical oxygen demand (COD) analyzers, and automated flow controllers. In some operations, treated effluent is reused internally for irrigation, ash quenching, or process water, further reducing the factory's environmental footprint. Solid waste is minimized through integrated process design. Soil and rocks from beet or cane washing are separated and sent to land reclamation or construction material applications. Boiler ash, as mentioned earlier, is either reused or compacted and safely landfilled. Filter cake from juice clarification, rich in organic matter and lime, is collected and sold as fertilizer, particularly in regions where soil pH management is important for crop health. Alongside waste handling and energy management, quality control is one of the most sophisticated systems operating inside a sugar plant. From raw material to final product, multiple checkpoints are established to measure, record, and verify key parameters. Quality assurance starts with raw material sampling. Upon arrival, cane or beets are tested for sucrose content, fiber, moisture, and purity. These values inform process adjustments and predict yield per ton of raw input. In the evaporation stage, bricks, soluble solids content, is measured at every effect using inline refractometers. These instruments use light refraction to instantly calculate sugar concentration in real time. Operators can adjust feed rates, heating input, or flow pressure based on these readings to maintain target consistency. During crystallization, samples are withdrawn at set intervals and examined under microscopes for crystal shape, size distribution, and purity. Technicians monitor the color using ICUMSA, International Commission for Uniform Methods of Sugar Analysis, standards, with high purity white sugar scoring under 45 ICUMSA units. If color values trend too high, indicating the presence of residual molasses, operators can make real-time adjustments to seeding rates or massacute concentration. After drying and cooling, sugar samples are run through particle size analyzers and moisture content meters. The particle size must fall within strict specifications depending on the final use. Granulated table sugar, for instance, has tighter specs than coarse industrial sugar destined for beverages or confections. Moisture content is typically targeted below 0.05% to ensure long shelf life and prevent clumping. Final color, purity, and turbidity tests are logged digitally and associated with specific batch codes for traceability. Packaged sugar is subjected to additional inspection. Bags, sacks, or containers are weighed using high-speed check weighers that verify fill accuracy to within plus or minus 0.2% of the labeled net weight. Vision systems inspect print clarity, barcode legibility, and seam integrity. Packages that fail any of these checks are diverted and manually reviewed. Silos storing finished sugar are equipped with real-time inventory monitoring systems using load cells and level sensors. Temperature and humidity are also monitored to prevent caking or condensation. In some regions, silos are also flushed with dry, filtered air to reduce microbial risk in high humidity climates. Across the plant, digital SCADA systems pull data from all production stages. Operators view real-time dashboards showing flow rates, temperature curves, impurity removal efficiency, and steam usage. These systems not only ensure daily operational control, but also provide long-term analytics for performance improvement. Advanced factories even deploy machine learning tools that analyze historical data to predict maintenance needs or recommend minor adjustments to maximize recovery rate and minimize energy consumption. To comply with food safety and export standards, many sugar factories operate under ISO 22000, FSSC 22000, or BRCGS certifications. This requires documented hazard analyses, allergen control programs, cleaning protocols, and traceability audits. Every production lot is labeled with a batch ID that connects back to a full production record: raw input, processing conditions, lab results, and packaging date. Customer-specific requirements are also programmed into the system. For example, pharmaceutical-grade sugar used in oral medications must meet even higher purity and microbial specifications and may be filtered again through fine mesh screens and sterilized using UV or ozone treatments before final packaging. In some cases, sugar is converted into liquid form, known as liquid sucrose or invert sugar, by dissolving granulated sugar in heated, purified water and, in the case of invert, breaking down sucrose into glucose and fructose using acid or enzymatic hydrolysis. These liquid sugars are pumped into sterile tankers or IBCs, intermediate bulk containers, and shipped under temperature-controlled conditions to manufacturers in the beverage, dairy, or baked goods industries. Even at this late stage, the role of the sugar factory is far from static. Engineers continue monitoring consumption trends, regulatory shifts on added sugars, and regional demand to adjust capacity and format offerings. New packaging materials, biodegradable options, and energy recovery systems are constantly being evaluated and trialed, keeping the entire facility in a state of adaptive optimization. With refined sugar now stored in silos, bulk bins, or sterile containers, depending on its intended form, the focus turns to distribution, packaging, and how this versatile ingredient is tailored to the requirements of a wide array of customers, from retail consumers to massive industrial clients. This final stage is no less complex than the upstream processing phases. In fact, it involves its own dedicated systems for handling, labeling, traceability, and product customization. At this point in the factory, packaging lines diverge into three main pathways: consumer packaging, industrial bulk packaging, and liquid sugar dispatch. Each line is specifically engineered for its product format, and all are equipped with high-speed automation and real-time quality assurance systems. For retail products, such as granulated white sugar sold in 1 kilogram or 2-pound paper bags, the packaging line begins by feeding dry sugar through a vibratory chute into a vertical form-fill seal machine. The sugar passes through a flow meter and enters a funnel that drops it into a pre-formed bag made from food-grade paper or composite film. These bags are formed, filled, and sealed in one continuous motion. The machine prints batch numbers, expiration dates, and sometimes QR codes or traceability data on each bag. Each filled package passes through a metal detector and X-ray scanner to ensure that no foreign objects are present. Then, check weighers confirm that the net content is accurate within a narrow margin. Any under or overweight packages are automatically rejected and flagged for operator review. The approved bags are collected into bundles, often shrink-wrapped into 10 packs, and sent to palletizers that stack them for warehouse distribution. For industrial customers, packaging formats differ significantly. Sugar may be packed into 25 kilogram woven polypropylene bags, 50 kilogram sacks, or even 1-ton bulk bags called FIBCs, flexible intermediate bulk containers. These bags are filled using gravity-fed hoppers mounted on load cells that ensure weight accuracy.